Welcome, everybody. So today we're going to talk about Ampere's law. Now, Ampere's law is kind of the magnetic equivalent of Gauss's law, which we covered a few weeks ago. Ampere's law says that the net magnetic field around a closed curve is equal to the current that passes through the region bounded by that curve. You can kind of see why it's an analog. If you remember back to when we did Gauss's law said the net electric flux through a closed surface is related to the charge enclosed. So now we just have magnetic field and we've got current instead of charge, and you'll notice that it's a curve and not a surface. And if you're not quite sure what that means, I've got a picture for you. This is right out of the book. And what you can see is there's a current which is running into the screen. And then there is a path which is labeled in black. It's a circle. And we already know what the magnetic field created by this current looks like. It's those blue arrows here. And so when I'm figuring out what the magnetic field around that loop is, I'm basically going to have to add up all of these little arrows all the way around the loop. It's a closed loop that I need to go around. So I have to, as this says, start and stop at the same point. Now, I chose a circle here, but it doesn't have to be a circle. It just has to be a closed path, right? So you can do a little weird squiggle, right? You can do a square. As long as you get back to the place that you started, that counts as a closed loop. You'll notice that this one, which we'll do an example of in a minute, has this really friendly behavior. The magnetic field is tangent to the path that we're going to go around the circle. That's really important because otherwise, as you can see, if you picked a path like this one, you can get a pretty unfriendly integral. And just like Gauss's law, it's not going to be super helpful. Right? So Ampere's law is only going to be helpful in a few specific situations. And what's valuable here is that because these two things are related, it can help solve a lot of helpful problems. All right, so I explained Ampere's law in words, and I've kind of shown you a picture of what it looks like. I want to give you the equation. And it actually maybe looks a little bit less scary than Gauss's law, if you remember back to it. So again, the left-hand side, net magnetic field around a closed curve. What we're really doing is finding the component of the magnetic field along a step of the path, and then adding up all of those magnetic fields as we take the steps along the path. That's the left-hand side. And then on the right-hand side, we just have to add up the current that's enclosed within the region. That's usually pretty easy. You just kind of count and say, 1, 2, 3, or I1 plus I2, or I plus or plus I3. Sometimes you might have a continuous distribution of current. Then you have to handle things a little more. All right, I want to do one example of this, which is kind of going to give us a result that we already know. So again, I'm going to look at the single current carrying wire. And again, I already know something about this magnetic field. The thing I know is that it points tangentially around the curve, and that's just from the symmetry of the situation. And I know that it's uniform along the path because I picked a circle. If I picked a square, magnetic field would change magnitude. So when I go to write down integral of b dot, I can't remember what letter I used there. I'm going to use dl right now, right? So dl, a little piece along the path. Then the dot product here is super simple because dl points in the direction along the path. In fact, if I wanted to, I could write this as dl is equal to, let's see, a little piece of arc length here is going to be the radius r of the circle times d theta, the little infinitesimal angle in the theta direction, right, pointing around the circle. And the magnetic field also points in the theta direction, so the dot product is going to give me 1. So I'm basically integrating a magnetic field, which is uniform, times a radius, which is also not changing as I go around the loop, d theta. And in physics, we always put limits of integration on here. So this is going to go from 0 to 2 pi, right? Once around the circle. Super easy integral here, right? B and r are constant. So this just gives me b times 2 pi r. And I'm using r here. I should really more properly be using s. The book uses r for this coordinate. But I think I'm going to change midstream here and call this thing an s, because that's more properly what it is, right? It's a cylindrical radius, not a spherical one. So 2 pi s, there we go. The other side of Ampere's law says that I take mu 0 and multiply it by the current enclosed, right? So I enclosed, and this is a super easy case because there's only one current in there, right? There it is, it's I. It points into the board. So I'm going to say that this is equal to mu naught I. Mu naught times I, and I can solve that for the magnetic field. So now I can figure out what the magnetic field strength is, right? Mu naught over 2 pi. And this is starting to look familiar, right? I divided by S, right? That's exactly the magnetic field due to a really long current carrying wire that we have been using for a week or so. Note that this didn't give us the direction. It only gave us the magnitude of the magnetic field, but we already knew the direction, right? So if you want to put this direction back in, you can go look up the appropriate cross product put here. So that's how Ampere's law works and how we can use it. If you pop back over to Top Hat, there's one last get ready question for you there. And then in class, we'll do another example where we can put this to use.